Welcome back to my channel. I'm Dr. Secure. Please join me as I demonstrate how to convert between binary and decimal numbers. As a cybersecurity professor at a 4-year university, I often explain some fundamental concepts before diving into more complicated topics. No matter what technical path you follow in cybersecurity or computing in general, you will need to understand binary. So let's get into binary conversion. But first, let's explain what binary is. Binary is the fundamental language of computing and digital systems because of its compatibility with electronic circuitry. In computing, information is processed using physical electronic components like transistors, diodes, and relays, which can exist in two states, on or off. On means electricity can pass through the physical wires, and off means there's a break or disconnect in the circuit, meaning the electricity cannot pass through. Think of when you flip a light switch on and off. When you flip the switch to on, the circuit is completed and the light turns on. When you flip the switch to off, you disconnect the circuit and the lights turn off. There is no in-between state. The circuit is either completed or it's not. The light is either on or it's off. Binary code consisting of zeros and ones aligns perfectly with this binary nature of electronic switches. Each single 0 or 1 represents 1 bit of data. 8 bits of data in a grouping is called a byte. The groupings are termed differently as more ones and zeros are needed. A kilobyte is equal to 1024 bytes. The prefix kilo is a factor of 1024 rather than 1000 because bytes are based in binary, base 2. A megabyte is equivalent to 1024 kilobytes, and a gigabyte is equivalent to 1024 megabytes. And by now you have seen a pattern. A terabyte is equal to 1024 gigabytes. So how do we represent those large numbers in binary? Well, mostly people are not going to write down a trillion zeros to represent a terabyte. Usually we will represent binary in powers of 2. For example, 1 kilobyte is 2 to the 10, 1 megabyte is 2 to the 20, 1 gigabyte is 2 to the 30, and 1 terabyte is 2 to the 40 bytes. We represent those long numbers in binary by adding more bits to the left. You will see what I mean by that shortly. In the world of binary, every bit is a switch representing on or off, and the combination of these bits allows us to represent complex information. In binary, the 1 represents on, and the 0 represents off. One easy way to remember this is, if the number is a 0, there is 0 power moving through the components, so 0 means the power is off. Ones and zeros are everywhere in everyday life. For example, take a look at the on-off switch of one of your electronic devices, like your coffee maker or vacuum cleaners. You will see a small 0 and 1 indicated on the on and off switch. Go ahead and test it out. See which way the switch flips and how the device turns on and off in alignment with the 1 and 0. Okay, now that you're done playing around, turning things on and off, let's continue. Unlike human languages with a large array of characters and rules, binary uses only 2 digits to represent all of those characters. This makes it easier for computers to process and manipulate data. While higher-level programming languages and applications may use more complex representations, they ultimately rely on the binary foundation. Binary code forms the basis of machine language and serves as the building blocks for more sophisticated programming languages and software. Essentially, every task a computer completes can be represented by a series of ones and zeros. Now I would like to provide a couple examples of binary to decimal conversion. I will eventually post more videos on converting from other number systems, such as hexadecimal, base 16, and octal, or base 8. Typically, if someone is going to assess your knowledge on these conversions, they will provide you with a number, what base it is in, and what base it should be converted to. In the first example, I'm providing 01110000 in binary, or base 2, to be converted to decimal, or base 10. The first step to convert binary to decimal is to understand the positional value of each digit. So first we write down the binary number 01110000. Next, I always write down a chart to refer to. Basically what you see is the binary numbers converted to decimal. The chart just shows the relation to the position of the 1 or 0 in the binary number to the equivalent decimal position. By creating a chart, it provides a quick reference as you perform the calculations. To create the chart, we will assign powers of 2 to each bit. Starting from the right, assign powers of 2. The rightmost bit is 2 to the 0, the next is 2 to the 1, then 2 to the 2, and so on, increasing the power of 2 as you move to the left. Since we have 8 bits, our powers of 2 will range from 2 to the 0 to 2 to the 7. Then what we're going to do is multiply each bit by the corresponding power of 2. So we will multiply each bit, 0 or 1, where it falls under. So we have 2 to the 0, which has a 0 under it. Anything times 0 is 0, so we'll carry down a 0. This is the same until we get to 2 to the 4. So we're just going to write these zeros. Then when we get to 2 to the 4, we see a 1 in binary. 2 to the 4, we're going to multiply that times 1. 2 to the 4 is 16, so 16 times 1 is 16. We write down a 16. Then the next one is 2 to the 5, which has a 1 underneath it. 2 to the 5 is 32. We can look at our chart. 32 times 1 is 32, so we write down a 32. 2 to the 6 is 64. We write down a 64. And the last one, 2 to the 7, is a 0. So we're just going to multiply that by 0, leaving us with 0. Then we're going to add up the results. So we're going to have 0 plus 64 plus 32 plus 16 plus 0 plus 0 plus 0 plus 0. We'll just drop all the zeros and we end up with 64 plus 32 plus 16. We add those together and we get 112. Now let's check our math. Here I have the calculator that comes with the Windows operating system, but both Mac and Linux have similar calculator features. The steps to access the calculator is a little bit different than what I'm showing you here. In Windows, to access the calculator, we're going to click on the Windows search bar at the bottom of your desktop and start typing in calculator. You should see it pop up in the list of available apps. I'll go ahead and click on that, and then the calculator should appear. Most calculators will show the standard calculator by default. If you click on the hamburger up at the top left, you can select programmer mode on the calculator. Now once you're in programmer mode, make sure you select the number type you are converting from on the left. In our case, we're starting with binary. So we click on binary and type in 0110000. You'll notice nothing pops up until I type in a 1 on the pad. That's because in binary, it is common practice to drop the leading zeros when we write it down. Of course, that is only the leading zeros. You cannot randomly drop zeros in the middle of a binary series. Now on the left you can see small numbers. It has the representation of our binary number in all the other supported formats, like hexadecimal and octal. So what we can see here is if we click on decimal, we can see that our binary number is equivalent to 112. Now let's try another. The binary number is 000111111. As in our last example, first thing we do is write down the binary number. Next, I create the chart that shows the decimal values of the binary number positions. Then we start our calculations. We're going to multiply each bit by the corresponding power of 2. So we multiply each bit, the 0 or 1, by the corresponding power of 2. 2 to the 0 has a 1 under it. Go ahead and look at our chart and see that 2 to the 0 is 1. So we multiply that by 1. 1 times 1 is 1. So we write down a 1 and move left. 2 to the 1 has a 1 under it. Looking at our chart, we see 2 to the 1 is 2. So we multiply 2 times 1 and that equals 2. So we write down a 2. 2 to the 2 has a 1 under it. We look at the chart, see 2 to 2 is 4. So 4 times 1 is 4. Write down the 4. 2 to the 3 has a 1, so we write down an 8. 2 to the 4 has a 1. Look at our chart, see 2 to the 4 is 16. 16 times 1 is 16, so we write down the 16. The remaining numbers are zeros, so anything times 0 is 0. So the remaining numbers are 0. These are the leading zeros, and we can drop those. Now we're going to add up our results. So from left to right, we have 16 plus 8 plus 4 plus 2 plus 1, which is going to give us 31. So that means that the binary number 000111111 is equal to decimal number 31. Let's check my math using the Windows calculator again. Click on the hamburger up at the top left to select programmer mode. I'll select the number type I'm converting from on the left. In our case, we're starting with binary. So if we click on binary and then type in 0001111, then click on decimal on the left, and you should see 31 in the display. Let's move on to converting decimal to binary. Many methods exist for these conversions, and you will still arrive at the correct answers. The method I'm showing you here is the easiest way for me to understand it. If the method I demonstrate here does not make sense to you, there are other methods you can try. If you want me to demonstrate one of those methods, please leave me a comment below and I'll see what I can do. Let's convert the decimal number 217 to binary. We are still working with powers of 2, so I will display my conversion chart again. I convert by subtracting the largest number from the chart that could be subtracted from the number provided, which is 217, without falling below 0. The rule for this method is that you keep subtracting the remainder until you reach 0. Starting with 217, we will look at the chart and we see the largest number in decimal is 128. As a side note, our next number, 2 to the 8, would be equal to 256. That exceeds 217. So we don't need to add another 1 or 0 to the left of 2 to the 7. If that doesn't make sense right now, it will in my next example, so hang in there. So what we'll do first here is we'll ask ourselves, is 217 greater than or equal to 128? Yes, it is. So let's write down a 1 under 2 to the 7 in the chart, and then we'll subtract 128 from 217, which will leave us with 89. So now looking at 89, is 89 greater than or equal to 64? Yes, it is. So let's write down a 1, and then 89 minus 64 is 25. Looking at a remainder of 25, is 25 greater than or equal to 32? No, it's not. So we're going to write a 0 down on the chart and look at our next number. Is 25 greater than or equal to 16? Yes, it is. Let's write a 1 in our chart and subtract 25 minus 16 is equal to 9. Is 9 greater than or equal to 8? Yes, it is. So we write down a 1 and then we take 9 minus 8 is equal to 1. Is 1 greater than or equal to 4? No, it isn't. Write down a 0. Is 1 greater than or equal to 2? No, it's not. Write down a 0 and move on to the right. Is 1 greater than or equal to 1? Yes! So let's write down a 1. Now 1 minus 1 is 0, so we're done. When we're done, if we look at our chart, we now see that 217 is binary. 217 in decimal is 1101101 in binary. I'm going to check my math again. I'll select the number type I'm converting from on the left. We're starting with decimal this time, so I'm clicking on decimal and typing in 217. Now click on binary on the left and we will see 1101101 on the display. This means that we performed our conversion correctly. This time I will show you what happens if we have a number larger than 255. Why 255, you ask? Because if you were to write down all zeros in binary, it would equal 0 in decimal. If you were to write down all ones in binary and convert to decimal using our single byte of data, it would equal 255. So let's say we were given a large number, like 792 for example. We will add zeros or ones to the left of the current place, which is 2 to the 7. So if we add 2 to the 8, which equals 256 in decimal, and 2 to the 9, which equals 512 in decimal, we should have added enough places to calculate the result. Our revised chart is shown here, so let's do the conversion using the same method as last time. Our provided decimal value is 792. Looking at the chart, we see 512 is the biggest number we have written down. Is 792 greater than or equal to 512? Yes, it's greater than. So we'll write a 1 under 2 to the 9, and then we'll subtract 512 from 792. That leaves us with 280. Is 280 greater than or equal to 256? Yes. So write down the 1 under 2 to the 8, and then subtract 280 minus 256, which is 24. Now let's compare 24 to our chart. We're looking for the value that could be subtracted from 24 without going into negative numbers. Scanning the chart. Yep, 2 to the 4 equals 16 and can be subtracted from 24 without going below 0. So we write a 1 under 2 to the 4 and zeros under the other numbers to the left of 2 to the 4. Then we calculate 24 minus 16, which is going to leave us with 8. Now we compare 8 to 2 to the 3, which is also 8. So 8 minus 8 is 0. We're going to write a 1 under 2 to the 3 and zeros under the remaining values to the right of 2 to the 3. When we are done, we will have a representation of 792 in binary, which is 110, 001, 1000. Let's check math again. I'll click on decimal and type 792. Then click on binary on the left, and we will see 0011, 00011, 000 on the display. This means that we performed our conversion correctly. So there you have it, converting from binary to decimal and from decimal to binary. Thanks for joining me today. If you found this video helpful, don't forget to like and subscribe. Leave a comment below if you have a particular cybersecurity topic you'd like to see next. Now go secure the digital frontier, and I'll see you in the next video. As a personal side note, I'm really enjoying putting these videos together, and I hope I can reach an audience that it will help. I'm very passionate about helping people succeed, so please feel free to reach out with questions or video requests. Thanks for watching.